All right, it's time for section 2.2. We're going to be talking about the graph of a function. All right, we often spend so much time thinking about equations, we forget about the graphs that are associated with said equations. So we're going to be talking about the vertical line test here first, and that's going to help us determine whether or not something is a function. All right, so a set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. Let me zoom in a little bit. At most one point. All right. This is a little Algebra 2 review for sure. So let's decide if these are functions, and then in either case, we're going to state the domain and the range. All righty. So this first one, we got ourselves a nice little quadratic. Passing the vertical line test, absolutely. It's only going to hit in one spot no matter where I draw that vertical line. So function. Check. All right, domain. Well, our domain, if we're going to be writing in interval notation, and I'll just go with that, we're going to have from negative infinity, because it never stops going to the left as it goes up, to positive infinity, because it never stops going to the right as it goes up. All right, then my range, well, my range, it looks like it's bottoming out at 0, 0. So my range is starting at 0, and then it goes up in both directions forever and ever. All right, got my domain and my range. Let's keep it moving. Over here, looks like we got ourselves likely a cubic function. Does it pass the vertical line test? Heck yeah, it does. All right, function. Check. Domain time. Well, my domain, does it ever stop going to the left as it goes down? No, sir. It keeps going, and it keeps going up and to the right. So my domain is negative infinity to positive infinity. And my range, well, my range, it keeps going down, and it keeps going up. So that means my range is the same thing here. It's going to be negative infinity to positive infinity. Excellent. My lights went out because it didn't notice me, and apparently I'm not tall enough to make it go, so I had to stand up. All righty. Next one. All right. This looks interesting here. All right. It's like it looks like that quadratic, but on its side. Does this pass the vertical line test? No. Not a function. And then domain and range. We can still do domain and range. Does it ever stop going to the left? Absolutely. It stops, it looks like at 0, 0, and then it continues back. So we're going from, for our domain, it's going to be from 0, including that point, because it is touching at the origin, to positive infinity. And then my range, well, my range for this one, as it goes down, does it ever stop going down as it goes to the right? Nope. And as it's going to the right again, it's still going up, right? So my range is from negative infinity to positive infinity. Okay, awesome. One last one here. We got ourselves a little, looks like a circle here with a consistent radius. So yep, circle for sure. Is it a function? Does it pass the vertical line test? It's hitting twice. Not a function. What's my domain here? Well, my domain, well, my axis, looks like I'm going as far as negative 3 to positive 3. And I believe I am including 3. And the same would go for my range. It goes as low as negative 3 and as high as positive 3. So with brackets again, my goodness. Boom. There we go. Awesome. All right. Let's keep it moving. So, want to obtain information from a graph of a function. Here we're going to get into some formalities of our wonderful pre-calc. It says if x comma y is a point on the graph of a function f, then y is the value of f at x. That is, y equals f of x. Okay, when I plug x in, I get y. When I plug a value in for x, I can get my y value. Also, if y equals f of x, then x comma y is a point on the graph of x. For example, we'll go into numbers here. Numbers usually help make sense. If 1 comma 9 is on the graph, then f of 1 is equal to 9. It's almost like a fancy way. This is like a fancy pre-calc way of writing an ordered pair, all right? So you do need to be familiar with that. And if f of 5 equals 4, then the point 5 comma 4 is on the graph of f, okay? Should say of f. There might be a couple typos here and there. I found one earlier. All right, cool. All right, so for this one here, we've got a graph. Looks like a cosine or sine function, depending on where you're starting from. I guess if we're starting from here, we're thinking this is more of like a cosine function. And it's been vertically stretched. I like it. Anywho, what are f of 0, f of 3 pi over 2, and f of 3 pi? So we're just finding the values based on the graph. All right, we're going to do a bunch of different exercises with this, it looks like. So f of 0. So if I plugged 0 in for x, that means I'm at this area. What's my y value? 4. So f of 0 is equal to 4. Okay. What's f of 3 pi over 2? I can even zoom in a little bit here. F of 3 pi over 2. Well, if I go to 3 pi over 2 for my x, my y value is 0. And lastly, when we're dealing with 3 pi, well, if I plug in 3 pi, I end up getting -4. Cool. All righty. We'll do more with graphs and getting values based on those things. It's very good to be able to handle graphs, tables, equations. They're all very important here, especially when you start getting into calculus as well beyond this. What is the domain of f? So if we're looking at the graph, what's the domain? Well, since this one doesn't have any arrows on the ends, we're assuming that it stops, okay? So my domain here is going to be from 0 all the way over to 4 pi. And that's all we're given here. It stops. So domain is from 0 to 4 pi, and it does include those points, so we're using brackets on that. All right? How about my range? Well, my range, it's fluctuating between -4 and 4, so my range is going to be from -4 to 4. And I am including those points. As you see, it does include that point. It's a solid dot there. All right. Let's see here. Part D, list the intercepts. All right. We've got a bunch. Why don't we start? We'll do the x's. It looks like we've got pi over 2, comma 0. I'm going to zoom out a little bit so I can see it all at once. There we go. So we've got x intercepts. We got pi over 2, comma 0. We have 3 pi over 2, comma 0, and 7 pi over 2, comma 0. All right. And then for my y-intercepts, there's only one here. There it is, 0, comma 4. All right. Since it is a point, I like to write it as an ordered pair. Some will accept just the x value or just the y value, but because it's a point on the graph, I'm writing it as an ordered pair. All right, part E, how often does the line y equals 2 intersect the graph? Well, first off, we got to remember what y equals 2 looks like, and it's easy to mix those things up. Y equals 2 is going to be this bad boy right there. It's a horizontal line. So how often does it intersect the graph? 1, 2, 3, and 4 times. 4 times. For what values of x is f of x equal to 4? Let's see here. When is this graph equal to 4? So when is the output value equal to 4? Well, that would be all up top here. So my x values would be 0, 2 pi, and 4 pi. For those values, if I plugged in 0, I would get 4. If I plugged in 2 pi to this function, I would get 4. And if I plug in 4 pi, I'd get 4. All right. For what values of x is f of x greater than 0? So when is my function above that x-axis, right? Not equal to it, just above it. So we're going to have a bit going on here. So it's above when it's this section here. Maybe I'll go ahead and outline it. I'll go green. So it's positive here, here, and here. That's when it's greater than 0. And all these things are going to tie into your later course of calculus if you decide to take that and identifying these parts of your graph. So super helpful now. All right. So it looks like I'm going from 0, including 0, so that is a point on the graph, to pi over 2, but I'm not going to include that because it's equal to 0 at that point. Then we're going to union with from 3 pi over 2, again, not including it because it's equal to 0 at that point, to 5 pi over 2, again with the parenthesis for the same reason. And then the last one, we're going to have 7 pi over 2 to 4 pi. And in this one, we do include it because it's a solid dot there, and it is greater than 0. All right. Not too bad. Now move on to example number 3. All righty. So consider the function. Now we're dealing with a function, an equation here for it. So x over x plus 1, rational functions. They're fantastic. We have is the point 1 comma 1/2 on the graph of f. Well, how can we figure that out? How about we plug it in? And I'm going to switch colors because I think it gets kind of monotonous when we do the same color the whole time. All right, we'll go red. So if I have f of 1 and I plug that in, I'm going to have 1 over 1 plus 1. So that it's going to give me 1 over 2. So is it on the graph? Yep. Awesome. So when I plugged 1 in, I got 1 over 2. That tells me that, that it is on the graph. All right. For x equals 2, what is f of x? And then what is this coordinate point on the graph of f? So if I do f of 2, that would be 2 over 2 plus 1, which is equal to 2 over 3. So f of 2 is equal to 2 over 3. That's what that's what f of x would be, right? F of 2 is 2 over 3. My coordinate would be 2 comma 2/3. Awesome. All righty. Let's keep it rolling. Feel free to pause at any time if we're moving a little fast here, guys, but I like to keep these videos as short as possible, just like Mr. Allen. That way you guys can get through them quicker if you're able to handle the speed. All righty. If f of x is equal to 2, what is x? And I feel like I want to have that equation still up there, so I'll leave it like this. So f of x is 2. What is x? So I want to get this to equal 2. I want 2 to be equal to x over x plus 1. And while this equation, I would say some of you might be able to just problem solve, guess, and check and get it, we could algebraically figure this out. So I'm going to multiply both sides by x plus 1 and this one by x plus 1. And we're going to end up canceling that, and I'll have 2 times x plus 1 is equal to x. So I've got 2x plus 2 equals x. I'm going to subtract the x and get x. I'm going to subtract the 2 and get negative 2. There we go. So that's what x is. What's the coordinate? Well, it'd be negative 2, comma 2 is the coordinate that's on the graph. Okay? So we're connecting this f of negative 2 equals 2 to the negative 2 comma 2 ordered pair, okay? So you'll sometimes see things written like this, f of negative 2 equals 2. This means the same thing as this ordered pair right here, okay? So you need to be familiar with those different notations. All right. What is the domain of f? We talked about this a bit. What's a no-no, if you will, when we're dealing with rationals? I cannot have 0 in the denominator. So let me set my denominator, x plus 1, equal to 0, which would give me x equals negative 1. So my domain in interval notation, which is what our book will ask us for, is negative infinity, comma negative 1, union, negative 1, comma infinity. There's my domain. Wonderful. And the last one, what are the x-intercepts of the graph of f, if any? What are these coordinates on the graph of f? Really, we're going to answer that one and the same. So my x-coordinates, well, my x-intercepts. What's happening on the graph when I'm crossing the x-axis here? What's my y value? My y value is 0, so my function value is 0. So if I were to take this and set it equal to 0, x over x plus 1, I want to get this to equal 0. Well, the only way I'm going to get this to equal 0 is if my numerator is 0. Okay? So if I had like 2x plus 5 in the numerator, I'd have to set that equal to 0 and solve. But I just have x in the numerator, so x is going to be equal to 0. So my x-intercept is going to be 0, comma, and if I plug that back in, I get 0. So there's my coordinates on the graph. All right, that's when this one is crossing the x-axis. And in fact, if it's crossing the x-axis at 0, 0, what's the y-intercept going to be? Let's still work it out. So when I'm crossing the y-axis, my x value is 0. So if I have f of 0, then 0 over 0 plus 1, that's 0 over 1, which equals 0. So again, it's 0, comma 0. You'll see if you get one of them is 0, 0, then the other one's going to be 0, 0 as well. It makes sense because they're both, each x and y is 0. Lovely. All right, we'll continue on. Hopefully you're handling this all right. If not, you can always pop in for some questions. Last problem here, and of course, love me some applications. So we're going to do a little bit of application here. Not a ton with it, but just a bit. So we have a Boeing 747 crosses the Atlantic Ocean, about 3,000 miles, with an airspeed of 500 miles per hour. Okay, that's the airspeed. The cost C in dollars per passenger is given by this, voice crack, I'm going to leave it, is given by C of x is equal to 1,000 plus x over 100 plus 3,600 over x, where x is the ground speed, which is your airspeed plus or minus your wind. So if you've got a headwind or tailwind, it'll affect your ground speed, okay? So determine the cost if the ground speed is 200 miles per hour and if it's 350. So what are we doing with that? I'm going to pop out my TI-84. I've been waiting to use this bad boy this whole time, all right? So if I plug in 200 miles per hour in for x, all right, if I plug that in, I'm going to get 1,020. So C of 200, and I'm just plugging this all in, 1,000 plus 200 over 100 plus 3,600 over 200. I'm going to get 1,020. So that's my cost if my ground speed is 200. That's the cost per passenger. Now, what if we up that to 350? So same idea, but I'm plugging in 350. I'll change markers here real quick. So C of 350, when I plug that all in, I end up with 1,013.7857, so we'll call it 0.8. That'll be my cost per passenger. All right. There we go, just a little bit of substitution. Now with domain on this one, we want to find the domain of C. We really love saving energy here. That's why these lights keep going out. All right, domain of C. With these application problems, you have to think a little bit beyond just the mathematics, right? There's really for our domain, if we're talking just normal stuff, we're just omitting 0, right? That's it. From negative infinity to 0 and 0 to infinity, because we just can't divide by 0. Everything else would work in this type of function. But we're not going to have a negative ground speed. That would be going backwards, I guess. You know, I don't think planes work that way. So at least not a 747 to my knowledge. So what I'm thinking here is our domain is it's gonna have to be larger than 0. So our domain is gonna be greater than 0. It can't be 0, it can't be negative. And because we don't really know enough information necessarily about this airplane, I'm just gonna throw that thing to infinity. Obviously, with an airplane, there's gonna be a top speed that it can go at flight, and there's also gonna be a low speed that a 747 can go, and I don't know what that is, but really that's realistically what we're looking at. But at least from what we know here, I'm going to restrict it from 0 to infinity. We're going to omit that negative side of this because that just doesn't make sense. All right. That's it for this one. Hopefully you guys are able to follow along. I know I was talking a little bit fast, but use that pause button to your advantage and jot some things down. Pop in and ask some questions. More than happy to answer some questions for you guys. Have a wonderful day. America, freedom, rock and roll. Yo, row. You only round once. and Costco, members only.